All right, let's see if we can use the washer method, but this time we're going to set it up to do vertical, and then I'll give an actual example where we compute it out. But I wanted to show you the different setups depending on where the axis of rotation is with respect to the region that you're rotating. So on the left here with our first example, we're going to have the axis of rotation to the left of where we have our region. Our region is trapped between the graph of y equals f of x, the graph of y equals g of x, and the x-axis. So this here is our little region. Notice that this is really not very good for doing a rotation any other way because we're rotating about the y-axis, which means we're spinning it this way. And so our shape when we rotate is going to have a shadow going out this way for g of x. And let's change color, the green one over here for f of x. Get it to match a little bit better. That'd be good. Right? And so when we spin about, we end up with this really strange looking shape. But we have now our washers are set up horizontally. So we have our green outer washer radius, and we're going to have our red inner radius. So this here is our washer. So our washer, here I'll shade it up so we can kind of see a little bit better, is going to grow and expand as it goes down and kind of contract as it goes up. So the point is we need to find a way to write the area of this washer as we integrate it starting from 0 and going all the way up to b. And unfortunately, to do this, our variable of integration is y. So the first step has to be to change these into functions of y. So assuming we were able to do it, that would mean that x is going to be f inverse applied to y. That'll be the outer. This will be for our outer boundary. And for our inner boundary, we're going to have x be the inverse function of y for g. So these are going to be expressions that you compute out, that you find, but they're going to be x as functions of y. They're going to look weird. But when we set up the integration, it's just like using the washers with respect to x. It's just that we integrate vertically instead of horizontally. So our volume setup is going to look precisely like it did before. The volume, this time we're going to integrate. We're going to start here for this picture at 0, go all the way up to b, 0 to b. Our variable of integration is going to be y because every time y changes, our disk changes in dimension. We're going to have pi times the outer radius, which is the green curve. That's given by the f graph, so it's going to be the f inverse, but it's not exactly the f graph because our axis cuts into it. It's going to be the f value, so this is where x is, but we have to take away this a because a cuts into that radius right here. So we're going to do the x value, which is f inverse of y, but this time we subtract a, and we're going to square it. So this represents the outer radius. And then for the inner radius, it's going to be very much similar, except this time we're just going from this dotted line to the g curve. And so it's the whole value of g without this a value. So we will subtract away pi times. And I'm writing it this way so you know it comes from g, but this is just going to be whatever the curve equation is with y's as your variable instead of x's. And again, we have to subtract a because it cuts into the radius length, and we square it. And we're doing this integral dy. Now, you remember how I kept telling you, you have to write dx, you have to write dy, you have to write dt? This is why. This tells you what is the variable that we're integrating with respect to. So having everything as functions of y here is crucial because we're doing a washer where our axis of rotation is vertical. So everything here happens with respect to y. Now I want to show you how different it looks in this picture here. What if the two curves are on the other side of the same axis of rotation A? Well, this time, this length is going to be added on. It's going to make the radius bigger by a factor of A. And the outer radius here is going to be my F, and the inside radius is going to be my G. So I'm going to have, if I draw out what this looks like, I've got my curvy part up top, and I've got my weird squiggle thing here happening below. And so my outside radius, my outer part of my washer, if I might say this height right here. So at this point, I have this piece beautifully. And then my inner part is going to do this piece. And so once again, I have a washer set up. I have the green outer part of the washer, and I have the red inner part of the washer. And now I just have to set out the boundary. The boundary this time is going to be the F inverse curve all the way to 0, right? So this x value plus this particular a value. So the outer radius here will be given the following way. So our volume, we're still going to integrate from 0 to b because that's still kind of what my y boundaries are. Y start at 0 and go to b. They could start somewhere else, but I'm just having them start at 0 for this. And then we're doing pi times the outer radius is going to be the one given by the f curve. So again, it's the inverse function. It's the one that has y as the variable. And this time we're going to add a because we add the length a to get all the way here. So it's going to be all of this. And then we're going to tack this on. But we want the actual distance. And right here, my function has a negative x radius. So I'm actually going to have to put a negative here to make it positive. So things get really dicey and weird when you're looking at where the curves are and what you have to add to them. So because we want a net positive distance, this here is going to be at a value x that's going to be negative, but I want to have the positive, so I have to put the negative in front. And then we add a and we square it. And now we're going to do the same thing for the red curve. The inner radius, we're going to have pi times negative g inverse of y plus a b squared y. So my point is, for all of these, you're going to have to draw the picture to see how the curve is affected and where it is. The reason why we have negatives that show up here is because the region we started with was on the left side of the axis. If I'd started with regions on the right side, I would have had positive values for my functions here. The reason why here we're adding plus is because the a adds to the radius instead of cutting into it. If we'd started with a region here for this same one, we would have had to subtract a. If, on the other hand, over here, my a were over on this side, I would have added a instead of subtracting. So depending on where your picture is, all of these can be pluses or minuses. That's why, since everything changes every time, it's crucial that we draw the picture to really decide where we are and what the radius is. Focusing on what that radius is the key to solving these. Now, I understand it's really ugly with all these f's and g's, so let me give you concrete examples so you can see how this works and how it's not so bad. All right, so what I'm going to do is I'm going to set up a triangle that I'm going to want to integrate. And my triangle is going to start here, and it's going to go here. So this is 1, 2, 3, 1, 2, 3, 4. And then it's going to go up to 3, and then it's going to come down here. So this is going to be the region that I'm going to rotate. And I'm going to rotate this about the x equals 1 axis. So this is the part that's going to spin. So when I draw my picture, this has an image that just kind of flips to right here. And so now I can draw my outer radius. So this here's the outer piece corresponding to this piece. And this here's my inner piece corresponding to this piece. And so for a particular y value, doesn't matter where you pick it, I'll pick it like right here. So I'm going to have my outside radius from my washer. It's going to go from here to all the way to here. And the inner piece of my washer is going to go this way. And so now we can see that we have a washer shape. And we're going to just integrate. We're going to go from 1 all the way up to 3 so that we get this entire piece exactly how we want it. Now you'll notice that here my inner radius is a constant. My inner radius is always going to be at the x value of 2. So this is going to be the constant x equals 2. It's always x equals 2. And x is still a function of y. So this x equals 2 changes with y, but it changes in a way that it's always the same. So this is going to be our inner radius. Well, no, it's not the inner radius. It's the inner line. The radius, though, is actually going to be from 1 to 2. So our inner radius will always be 1 here. The outer radius is the one that's going to change. Now, if we look at what this line is, you'll notice that it has a slope of, when we go, change in y is 2, change of x is 1. So it has a slope of -2. And it goes through the points, say, 2, 3. And it goes through 2, 3. So I can use my skills from algebra to find what this line is. It's y minus 3 equals -2, x minus 2. I'm using the point slope form. And since we want to solve this for x anyway, I'm not going to bother to put it into y-intercept form. I'm going to divide everything by -2, and then I'll be able to add 2 afterwards. So I get -1/2 y plus 3/2 equals x minus 2. And now I'm just going to add 2 to both sides. And so here I get x equals -1/2 y. And then when I add 2 to 3/2, I'm adding another 4/2 to it. So that's going to be plus 7/2. So this is going to be my function, x as a function of y, for the outer line. And so now my outer radius is just going to be this line, but -1. So outer radius is going to be -1/2 y plus 7/2 minus 1. So now we have our inner radius, we have our outer radius, and we can set up the volume. The volume is going to be the integral where we start y at 1 and we go up to 3. We do pi times the outer radius squared, which is going to be -1/2 y plus 5/2, because 7/2 minus 1 is 5/2. We're going to square this, and then we're going to subtract the pi times the inner radius squared, which is just 1 squared. And we're integrating dy. So we can just pull out the pi